Good morning, students. So, while I was discussing about dynamic programming, I showed you how that the dynamic programming paradigm can be used to solve certain graph problems, like the computation of all pair shortest paths. So, likewise, you can use the greedy paradigm also to compute a lot of graph problems. So, to motivate ourselves, we will talk first about a special type of graph problem, which is to find minimum spanning trees. Suppose that there is so let us take a realistic example. Say there is an urban planner, okay, so who wants to connect certain cities by roads, okay. So this is the task, okay. So you want to connect the different cities by roads, so that driving from one city to the other is possible. So this is the objective, okay. However, in order to achieve this objective, the urban planner is constrained by budgetary restrictions. Okay, so the urban planner is actually constrained by the budgetary restrictions. Now, therefore, what the urban planner might want to do is to use the minimum amount of road. That is what he would want to build. Okay, he would want to build the minimum amount of road in order to be within budget. Okay, so this is exactly the problem that the urban planner has to solve. Now this problem actually can be very nicely mapped to spanning trees in graphs. Okay, so let us define to begin with what is a spanning tree. So a spanning tree of a graph G is a connected subgraph that contains all the vertices in G and is a tree. Okay, so it will contain all the vertices. This is a special type of subgraph that will contain all the vertices in G and is a tree. Okay, so for example, okay, so let us define the next concept before we go to seeing an example. So a connected subgraph, okay, of minimum weight, okay, a connected subgraph of minimum weight having all the vertices and is a tree is a minimum spanning tree. So these weights are on the edges, and imagine that this actually indicate the amount of road that needs to be built by the urban planner to connect the different cities. Okay, so therefore a minimum spanning tree, in other words, a minimum spanning tree is a spanning tree with minimum weight. That is what you define as minimum spanning tree. So again, it is a connected subgraph of minimum weight having all the vertices and is a tree. So this having all the vertices and is a tree is nothing but a spanning tree, and we want a spanning tree of minimum weight, which is called the minimum spanning tree. So let us take an example to understand this concept better. Let us say that we have a graph okay. Let's say that this is an input graph, okay. So you can construct various spanning trees from this graph. One example is remember, it should be connected, it should be a tree, and it should have all the nodes of the original graph. So this is a spanning tree of the graph G. However, this is not a spanning tree of minimum weight, because there exists something which has a weight lesser than this. So one example of a minimum spanning tree formed from this graph is the following. See, the total weight here is 6, 3, 9, 10, 15. Okay. Whereas the total weight here is 4, 3, 7, 8 to 10. Okay. So this is one of the minimum spanning trees, and you cannot get something better than weight 10 for this particular graph. Okay, so this is one of the minimum spanning trees of this graph. There is one more, and your homework is to find the other minimum spanning tree. Okay, so this one is one spanning tree, and there is another one which is of exactly equal weight and is also a spanning tree. Okay, just find out that, and that's a homework. So this will make the idea more clear. Now our task at hand is to find a minimum spanning tree of a graph G. Okay, this is what we want to find. Given an input graph G, we want to find out the spanning tree of that graph. Can we have a solution for this? Seems like that we can actually have a greedy solution for this problem. Now, for this particular problem, let us assume that G denotes the graph as usual, T denotes the spanning tree, okay, and the vertices of T are the same as that of G. Okay. However, the edges F of T are a subset of the edges of G. So this implies T is a subset of E. Okay. And we will denote F is a subset of E. And we will denote the spanning tree T as V, comma F. Okay. So a very high level greedy algorithm for this particular problem can be written as follows. We initialize the set of edges to null. Okay. Now, while the instance is not solved, select an edge according to some locally optimal condition. So you probably very well appreciate that this is the selection procedure of the greedy algorithm. Okay. Now, if adding the edge if does not create a cycle, because we have been told that it has to be a tree. Okay, so it cannot have a cycle. Then add it. Okay, so therefore, again, I hope you can appreciate that this is the feasibility check. And then finally, if is a spanning tree, the instance is solved. Okay, so this is the traditional solution check. So this is a very top level, I mean, like 10,000 feet overview of the greedy approach to solve this problem. Now there are various important placeholders which we'll have to answer one by one. So now, as you see, one of the statements in this top level algorithm says that select an edge according to some locally optimal consideration. Now, how do you decide what is a locally optimal situation? Okay, what is that local optimal property that you are going to look into? Okay, so it turns out that there is no single local optimal property, not a single such property. So there can be more than one such locally optimal property that one can choose. And depending on what you choose, there are at least two existing known algorithms, okay, which are very, very famous in the graph algorithm literature. One is called the Prim's algorithm, and the other is called the Kruskal's algorithm. Okay, at least there are two well-known ways of choosing the locally optimal property, and based on how you choose it, you get the two algorithms, either the Prim or the Kruskal. Okay, so we will start with the Prim's algorithm. Okay, so again we assume that F is empty in this case. Now let us also consider that Y is a subset of vertices that is initialized to, let's say, V1. Okay. Now a vertex nearest to y, okay, is a vertex from v minus y that is connected to a vertex in y by an edge of minimum weight. Okay, so that is how you define the nearest vertex. So you have a set y which can be initialized to v1, and then we will see how you increment this set. Okay, and the vertex uh, from v minus 1 is said to be nearest to y if it is having the minimum edge weight, okay, from a vertex in y. So if we again recall the figure, it will be easier for us to understand this. Let us draw the figure once again. So this was our initial graph. Okay. Now, as we said that if we set y to v1 initially, then the vertex nearest to y is, so the nearest vertex to y, since y is v1, the nearest vertex to y should be v2, right? So is v2. So the vertex nearest to y is added to y, and the edge with minimum weight that we just now found is added to f. Okay. So therefore, in this case, v2 is added to y, and the edge v1 v2 is added to f. Okay. And this continues until and unless y is equal to v. That is, you have been able to cover all the vertices. So this in a nutshell is the Prim's algorithm. Now we can write a little bit better formulation of the Prim's algorithm. Now the 10,000 feet overview will change into a 1,000 feet overview. While the instance is not solved, select a vertex from v minus y that is nearest to y. Add the vertex to y, add the edge to f if y is same as v, the instance is solved. So you see that here both the selection procedure and the feasibility check is having a single statement check. Okay, so this statement actually does both the selection, okay, as well as the feasibility check. How? Because see, since you are always choosing the candidate vertex from v minus y, this ensures that no cycle can be formed, because whatever is there in y is not being considered when you select a new vertex. You only consider vertices that are present in v minus 1 y, and therefore there is no question of repetition of vertices in y, and therefore no cycle can be formed. That actually ensures the feasibility check. And the other part, which tells you to take the nearest vertex to y, actually is asking us, is helping us to enable the selection procedure. So both of these tasks are done simultaneously using this single statement. And then finally, when you have incorporated all the nodes in y, the instance is solved. So we can quickly walk through an example, okay, of how we can construct a spanning tree using the Prim's algorithm. Let's again take the running example of the graph. Okay, so in this way we can start the procedure that our vertex v1 is selected. Okay, the first vertex to be selected is v1. Now we will have to find the nearest vertex to v1, and in this case the nearest vertex to v1 is v2. So therefore in the next step we will have both V1 and V2 selected. So now we have selected both V1 and V2. Okay. Next, so recall at this point our Y set has two entries, V1 as well as V2. Now we will have to find out the nearest of these two vertices taken together one by one from the rest of the vertices. Okay. So now you find out, you can find out nearest of V1. So now the rest is V minus Y, which is V3, V4, V5. Now the nearest of V1 is V3, which is weight 3. Okay, and the nearest of V2 is V3 again, which is of weight 3. Now both of these are of weight 3, and therefore this is also the minimum weight. In this kind of cases where there is a tie, we arbitrarily choose one of them. And now you see, like, this is where you have the possibility of multiple minimum spanning trees. We could choose this one, we could choose this one, any one of this is okay. If we choose this one, then we leave out this one, and if we choose this one, then we leave out this one. But in both cases we will obtain a minimum spanning tree, and these are the two variants of the minimum spanning tree which I was asking you already to do as a homework, but okay, it has come out naturally. So let's, so the nearest now is V3. So in the next step, so we have taken V1, V2, V3. Okay. At this point, our Y is the status of y is v1, v2, v3. Now we have 3 nodes, and from here again we will have to find the nearest. Okay, so we will see from v1 which is nearest. So there is no other node which is connected to v1 and is in v minus y, right? So therefore v1 is out of question. Now for v2 we have v2 to v5, okay, and v2 to v4. Out of this, v2 to v5 is the minimum, okay. And for uh, v sorry for I'm sorry for v3 we have v3 to v5 and v3 to v4. Out of this, v3 to v5 is the minimum. Now from v2 we have v2 to v4 only. There is no other node which is in v minus y and is connected to v2. So therefore for v3 we have 2 options, v4 and v5. Out of this we will choose v5 because that has a minimum, or that is nearest, has a minimum weight. Okay, so we have now taken all the vertices up to v1, v2, v3 and v4. Okay, only v5 is left. Sorry, v1, v2, v3 and v5 we have taken, only v4 is left. Okay, so now at this point our y is and then in the final step we will include v4. Okay, we will visit v4. In this step all the vertices get visited. Okay, and now my y is equal to v. Okay, and I have also, while coming through the course of this visits, I have also kept on storing my edges from where I can get the final tree. So the final tree I had already showed you earlier. So your final tree will be as per our current traversal, your final tree will be this will be our final MST. Okay. However, if we would have arbitrated on the other edge, then the other MST would have been, if we would have chosen the V2, V3 edge, then the other MST would have been the following. And you see the cost of both these MSTs are exactly the same. This is also 10. This is also 10. Okay. So in this way, you actually obtain the minimum spanning tree using the Prim's algorithm. Now, all this time, the entire algorithm was written in a very hand-wavy manner. Now we will try to formalize this algorithm in a little more C-style way, C-style pseudocode. Okay. So as we had done earlier, let us call Wij as the matrix, the weighted adjacency matrix. Okay. So that is as simple as that. Along with this, we will also introduce two more data structures: nearest I, which is the index of the vertex in Y, nearest to Vi. Okay. And then there is distance I, which is the weight on edge between Vi, and the vertex indexed by nearest I. So I guess you are already appreciating that we are trying to keep track of the nearest vertex and the distance of the or the weights of the edges, okay, between any vi and the vertex indexed by nearest I. So if we assume that y is v1, then nearest I is initialized to 1. Okay, so this is the nearest index of the vertex. Okay, this is the index of the vertex in y that is nearest to vi. So here this would mean the interpretation would be that v1 is the nearest vertex to itself. Okay, so that's why the nearest I in this case should be 1. Okay, so you read it like when y is equal to v1, you read it as the vertex nearest to v1, that is v1 itself. Okay, the nearest vertex to v1 is v1 itself. Therefore, nearest I is initialized to 1. Okay, and distance I is initialized to the weights on the edges between the vertex in nearest I, that is v1, and all the vi's. Okay. So as new vertices are added to y, these two arrays, the distance I and the nearest I, both of them get updated, okay, with reference to the new vertex. Okay, now to determine which vertex to add to y, like earlier we were doing it like, mentally, but the computer has to do it in some way. So in order to determine which vertex to add to y next, okay, in each iteration we compute the index for which distance I is the smallest. Okay. And we call this index as a special variable v near. Okay. We call this index to be v near. Okay. And as soon as v near is added, so once v near is added to I, what is my immediate next step? I will set distance v near to -1, because this would ensure that this vertex is not considered again, thus preventing cycle formation. Okay. So now, given all this paraphernalia, let us see how we can write a C-style pseudocode. Problem is to determine a minimum spanning tree. Inputs integer n larger than 2, okay, where n is the number of nodes, a connected weighted graph, weighted undirected graph, okay, of n vertices represented by the matrix Wij, where both I and j run up to n. Output a set of edges f in a minimum spanning tree. So we proceed to write the pseudocode. It's a very simple pseudocode. Set of edges is a special data structure where we store the edges. all the initializations go here. Now we start with an empty set of edges. First we initialize the nearest I is set to V1, okay, for all i's, and distance I is set to the weights of the edges from node 1 to all the other vertices. Okay, as we had already discussed. Now we repeat as long as there are nodes n-1 times the following. Let us set mean to infinity. Okay. Now for I equals to I less than equal to n, I plus plus, if 0 is less than equal to distance I is less than mean. If the distance is less than mean, then you set mean to the distance I and V near, which is the nearest vertex to Y, and which is a candidate to be inserted to Y to this index. Okay. Now E is set to the edge connecting vertices indexed by V near and nearest V near. Because V near is our minimum distance vertex, so we take that edge which is like having the minimum weight, and that edge would be the edge between V near and the nearest V near. Okay. Add E to F. At this point, you immediately make distance V near is equal to -1, so that this vertex is not considered anymore. Now you have to add the vertex V near to Y. Okay, that part is left, and accordingly update the two data structures, nearest and distance. For I equals to I less than equal to n, I plus plus, if wi v near is less than distance I, then you make distance I to the minimum weight. So it was earlier some weight that was distance I, okay. Now it has been updated with wi v near if wi v near is less than distance I, and nearest I, this is where you are placing the vertex into the new vertex into y. The nearest I is placed in v near. As simple as that. Okay, so you have three parts. In the first part you have, you know, initialized y to v1 and set all the distances to distance from v1. Okay, this is the second part. The third part, sorry, the first, this is the first part. The second part is where you are obtaining v near. Okay, by finding out the minimum among all the distance values. Okay, and the index that gives the minimum among all the distance values is also set to v near. Okay, so this is where you are remembering the minimum distance vertex, okay, from y. So this is the minimum distance vertex from y. Now you are adding the edge, and then finally you are adding this minimum distance vertex back to y and updating the distance and the nearest data structures accordingly. So this is the, in a nutshell, the algorithm to achieve the minimum spanning tree using the Prim's method. Okay. Now the time complexity is simple. You can obtain an every case time complexity. Okay. So the outer loop that goes n minus 1 times, right? Okay. So the outer repeat that goes n minus 1 times. Now, then what happens? So inside this, you have again an inner loop going n minus 1 times. Okay. And everything that happens inside this inner loop can be considered to be as basic ops. Okay. So it could be the estimation of v near, or it could be the update of y. Both of them takes similar amount of time. So any one of them can be considered to be as the basic of. Okay, there are actually, if you see within the outer n minus 1 loop, there are two inner n minus 1 loop. Okay, so there are two inner n minus 1 loops. One, let's make it clear, two inner loops going n minus 1 times each. Okay, so one is for estimation of linear and the other is update of y. Okay, you can consider any one of these as uh, a tool to compute the uh, complexity. If you consider any one of these, you will get the same complexity. So basically your Tn will be n minus 1 into n minus 1, and this is 2 times, right? Inside loop has two n minus 1s, so that is big O n square. So this is how you write the formal description of the Prim's algorithm and also obtain the time complexity. Now, the question that still remains to be resolved is whether this is an optimal algorithm. That is, whether it is guaranteed to always give the minimum spanning tree. Because it's a greedy algorithm, we have to still prove that it always will result, if you take these greedy steps, it will always result into a minimum spanning tree. So we will do this in the next class.